Okay, so we want to look at how we go about finding the form of the rate law and exactly what finding the form of the rate law actually means. The most common method to find the form of the rate law is referred to as the method of initial rates. And in this method, what you do is you have some way set up that you can find the initial rate very soon after the reaction has started. Then you do several experiments with different concentrations, and you compare these different experiments so that you can determine what effect each change in concentration has on the rate. So after you have done the experiment, then what you will have calculated or discovered is what the value of these numbers are, and these should actually be exponents instead of written as they are. And then you also find the value of the rate constant, and this is always dependent on temperature, so all of the rate information that you find is only true for a particular temperature. Okay. When we talk about the overall reaction order, what we mean is the sum of the exponents, and in general that could be more than 2, it could be 1 or 2 or 3, whatever. And then that enables us, once we have the form of the equation, then for any particular set of concentrations we can find what the rate would be. This is limited because the rate is always changing, because the rate depends on the concentration. So while this is useful to find the order of the reaction, it's not, in a practical sense, useful to find out how long it's going to take for a reaction to reach a certain concentration. One of the things that I think I mentioned in the previous video is that there is no relationship in general between the order, that is the exponents in the rate laws, to the coefficients from the balanced equation. And we will see why that's true soon, but essentially it's because that most reactions take place in several steps, and it's those individual steps, or at least one of those individual steps, that determines the actual rate of the reaction. So I will explain that sort of enigmatic statement in a little bit. Now we're going to take a look at a first order reaction, and the general representation for a first order reaction is this. So you have rate equals a constant times just a single component, and its concentration raised just to the first power. If we integrate this equation, then we end up with a form that looks like this. And in this case, what we have is the value here. This is the concentration. This is a constant. This is time. And then this is the natural log of the concentration at an initial point. Actually, I should have said that this concentration corresponds to the concentration at this time t. There are another couple of points that I would like to make about this form of the equation. So first of all, that if you look at this form here, it is in the same form of a linear equation. So y equals mx plus b, okay, where m is the slope and the slope equals minus k. So that's one point I want to make, and we'll talk about why that matters in a minute. The other is that we can rearrange this equation, which we typically do when we solve it. So what I'm going to do is get the ratio of the concentrations on the left side and then the other information on the right side. So when I do that, I'll have Ln, and then this is going to be the initial concentration over Ln. This is the concentration at a later time. I'm not going to put t down there, but it's at time t. And then because I moved things around, then I've lost the negative sign, so this is just going to be kt. So this is the more typical form that we use when we solve this equation. We saw in the previous slide that for a first order reaction, that is one in which rate equals K, concentration of T raised to the first power, that it takes the form y equals mx plus b. So what that means is that if we plot here the concentration versus time, we get a straight line, and the slope of this line, or let me put it differently, let me say that k equals minus the slope of this line. So if you look back at the equation that we had a moment ago, then you'll see that this is the case. So this is an experimental, or it gives us a way to conduct an experiment and find both the order of the reaction and the slope. So we do the experiment, we plot the how the concentration changes, or how the natural log of the concentration changes over time. And if we get a straight line, then we know it's first order, and then we know that k is going to be equal to the minus slope. And you may say, well, what if you don't get a straight line? So we'll talk about that situation before long. So one useful idea comes out of the first order rate equation, the integrated first order rate equation, and that is the idea of half-life. So if we think about this, so let's say that we start off, and let's say we have whatever the concentration is, but we'll call that initial concentration 100%. And then after some time we have half as much left, so that's 50%, and that equals Kt. So really what we're doing is we're doing ln of 2, right, and that's equal to Kt. So ln of 2 is equal to 0.693, which equals Kt. And then if we rearrange the equation, we get the form over here, which is the most typical form. Now, the other interesting point about this is you see that concentration is not part of this equation, and the reason is because the half-life doesn't depend on concentration. Half-life actually only depends on what the value of the rate constant is. So this is something that we also use quite a bit, especially in nuclear chemistry, which we may or may not get around to talking about. But I'm sure you've heard the expression half-life, and this is where it comes from. Okay, let's see if we can work this problem. So we've got a first order reaction. We are told that it's 35% complete at the end of 55 minutes, and we want to find the value of K. So let's first write our equation. So Ln okay. All right. So we aren't told about the initial concentration, but of course we will assume, given the problem, that it's 100%. Let's go ahead and just, it doesn't really matter, but let's just call that 1. And then if it's 35% complete, that means that it's 65% incomplete. So that means you have 0.65 left, okay? And we're trying to solve for this, for K, and then we also know that this is 55. And I'll go ahead and put minutes down there. So Ln of 1 over 0.65 is 0.4308. So this is 0.4308, and then we're going to divide by 55 minutes. And I didn't actually write down 0.4308, I just took the number that was in my calculator. So when you do that, you're going to get 0.00783, and the units are minutes. It's very common to write this like this. Like that. Okay, so you'll have more practice on the owls, but let's just sort of look at the situation that we have here. So here are the different things. You can know any of 1, 2, 3, so any 3 of those 4 and find the other one. So again, you'll have some practice problems in the owls doing this. In the next video, we will take a look at how this how the rate equation, the integrated form of the rate equation, works out when we have zero-order reactions and second-order reactions. And then finally, we will compare the zero, first, and second-order reactions and see how we can distinguish between the three.